Good morning, student. Today we'll solve some numerical and we'll discuss the block diagram reduction. Okay, so we have to obtain the transfer function of the mechanical system, which is shown in this figure. Okay, so the output of this angular displacement output is the angular displacement theta of the shaft on the output side, and theta 1 is the angular displacement of the shaft on the input side. Okay, we have to draw the mechanical network, equivalent mechanical network. So what is the procedure? Procedure is we have to first see how many displacement are there, angular displacement are there. So there are two angular displacement are there. So this is theta 1. So two nodes will be there. And between this theta 1 and theta, this spring element is there. Okay, and there is one reference line. This is a reference line, and between this theta 1 and reference, this element is connected, inertia element, and the torque is applied. Between theta and the reference, there is again J2 element, and again there is a coefficient of friction F. Okay, so this is a equivalent mechanical networks. Now once you draw the equivalent mechanical networks, our next aim is to so we have to write the torque equation for this. We have to write the torque equation for this in place of the force equation, because this is a equivalent mechanical networks, and we have to write the torque equation for this. So apply the Newton's law at this theta 1 at node theta 1. So P of t is equal to J1 d square theta 1 by dt square plus this spring element is connected between theta 1 and theta. Okay, so this is equation number 1. We can solve this equation further. P of t is equal to J into d square theta 1 by dt square plus k theta 1 minus k theta. So this is equation number 1. Now we have to also write the torque equation at this node theta. So again, this element, a spring element is connected to this node. This inertia element J2 is connected, and this damper F is connected. So three elements are connected, and the force is not at this node. There is no force at this node, and therefore force is torque is equal to 0 here. So second equation, torque is equal to 0 and n into theta minus theta 1. Plus J2, this is J1, d square theta by dt square plus F into d theta by dt. This is your equation number. We can solve this equation further. K theta minus k theta 1 plus J2 t square theta by dt square plus f into d theta by dt. This is equation number 2. Okay. Now we have to take the Laplace transform of equation 1 and 2. Take Laplace transform of above equation 1 and 2. So T of S is equal to J1. This is a S square theta 1 of S plus K into theta 1 of S minus K into theta of S. So this is equation number 3. So we'll take here theta 1 of S on one side. So J1 S square plus K theta 1 of S minus K theta of S P of S. So this is equation number 3. Again, we take the Laplace transform of equation 2. Laplace transform of equation 2 gives K into theta of S minus K into theta 1 of S plus J2 into S square theta of S plus F into S theta of S. Okay, so this is the Laplace transform of equation 2. Again, we have to take here theta J2 S square plus F of S plus K. This is theta of S minus K into theta 1 of S. This is equation number 4. So from equation number we can write like this. So here now we have to write the equations we have to find the transfer function. Transfer function is nothing but this is theta of S by T of S. So this is a transfer function. So the transfer function now we have to write this T of S is equal to the first after the equation number 3 we can see here and equation number 4 we can see here. Now here we have to find the value of theta 1 of S and that theta of 1 of S we have to put into the equation number 3. So from this we can find the theta 1 of S. So this theta of S, theta 1 of S is equal to J to S square plus F of S plus K divided by T. This is the value of theta 1 of S. So this theta of 1 of S we have to put in this equation number 3. We have to put in equation number 3 and therefore T of S is equal to J1 S square plus K J1 S square plus K into theta 1 of S. So this is a theta 1 of S J2 S square plus FSK by K minus K theta of S minus K theta of S. Okay. So here now we have to we have both the terms that is T of S and theta of S. Now we have to just put this equation in this form. theta of s by t of s, and that will be your transfer function. That will be your transfer function. We have to solve this equation further. So how you can solve this further? Now we will take outside here the theta of s, here theta of s. So here it is a theta of s. Okay, so theta 1 of s is equal to this factor divided by k. So here theta of s will be there. Okay, so what we'll do, we will j1 s square plus k j2 s square plus f of s plus k, and minus, what we'll do, we'll take here outside k square is theta of s by k. We have taken this theta of s by k outside. So when you take theta of k, okay, so now it is okay. We have to now solve this j1 j2 s raised to power 4 plus j1 f s raised to power 3 j1 f s raised to power 3 plus j1 k s square, okay, plus j2 k s square plus f k s plus k square minus k square into theta of s by k. So this k square will get cancelled. Now we can write here okay, this is a t of s is equal to is j1 j2 s raised to power 4 plus j1 f s cube plus here we can take k outside, so what will be there, j1 plus j2 ks square plus fks into theta of s by k. Now we will write in the transfer function form. What is transfer function? That is theta of s by ts. So if you take theta of s on this side, and this k will be go into the numerator, and this will come into the denominator, that is j1 j2 s raised to power 4 j1 f s cube plus j1 plus j2 k s square plus fks. So this is the transfer function. So this k upon j1 j2 s raised to power 4 plus j1 f s raised to power 3 plus j1 j2 k s square plus q. So this is a transfer function. So this is a required transfer function. Next is the block diagram reduction techniques. So it is a when to use the block diagram. Whenever it is a simple block diagram are there, then we can easily find the transfer function by reducing the block to the single block. But whenever it is a complicated block diagram, then it is very necessary that we have to use some rules. There are the rules for the block diagram reduction techniques. So it is important that a block can be connected in series or in parallel. Okay. So if the output of one block is not affected by the next following block, and if there are any loading effect between the components, it is necessary to combine these components into the single block. So any number of cascadal blocks representing non-loading components can be replaced by the single block. So the complicated block diagram involving many feedback loops can be simplified by the step-by-step arrangements using the rules of the block diagram algebra. So there are some important rules are there. So this if you use these rules, will definitely solve the block diagram techniques. So important rules for the block diagram reduction techniques. Rules for block diagram reduction. So when suppose the two blocks are there, these two blocks are there, and the gain of these blocks are, suppose gain is G1 and gain is G2, and this is the incoming signal to this block X1. So what is the output here? Output is nothing but the gain of this block into the coming signal. So it is a X1 G1. So what is the output here? At this end, it is X1 G1 G2. So this we can represent by just one block. The above two blocks can be represented by just one block by representing like this G1 G2, and this is in the end X1 G1 G2. So this is when the blocks are in cascade. The first rule is when the blocks are in cascade or in series. Cascade or in series. Okay. Now second block, when the blocks are in parallel. Combining blocks are in parallel. Combining blocks in parallel. So initially the two blocks were in series, now it is in parallel. So parallel blocks are, suppose having the blocks are connected like this. The gain of this block is G1, G2, G2, and these are connected like this. And these are added at this point. So these block, if the two blocks are connected in parallel and they are again added at the summing point, okay, so what will be this X2? So this can be represented by only one block, and it is a G1 plus minus G2, and this is X1 and this is X2. So in this way, these two blocks which are in parallel, they can be reduced by only one blocks, and the gain of that block is just the addition of the individual gain. Okay, G1 plus minus G2. So in this way we can add these two blocks in parallel. So moving a summing point after a block. Now third rule, moving a summing point after a block. So summing point is there. So suppose this summing point is there. This is summing point, and what this is the block having the gain G, and this is the feedback loop. The signal coming from this feedback loop is x2. From the input side it is x1. Okay, this is a plus. Now here it is a x1 is added with this x2 and it is multiplied by G, and what will get here? G into x1 plus minus x2. Okay, so in this way you should get the output at this, but here we have to move a summing point after a block. If you move this summing point after the block, the output should not change. So the summing point after the block means this is G and this is a summing point. So what is x1 is there? So at this end it is a G1, sorry, it is Gx. It is a Gx. So this G into x1. But at the output end, what should be there? G1 into x1 plus minus x2. So we are getting, now if you add here, what will be there? G1 G1 x1 plus minus x2. Whether this is same to this? No. Here should be also G. Okay. So that what we'll do? We will add one more block in the feedback loop, and the gain of that block will be G. Now it is okay. So on this side it is x1G, on this side it is a Gx2, so that output will be same. Output will be G into x1 plus minus x2. So in this way we can shift, we have shifted this summing point after the block, and there is no effect on the output of the systems. Output is remaining as it is. So this is how we can reduce the complicated block for the sake of the simplification purpose, either just by moving the summing point after the block or before the block. Now the next rule is moving a summing point ahead of the block. Moving a summing point ahead of a block means, see, this is the gain one block and this is a summing point is there. So this is x1 input signal. So what will be here? It is x1G. There is one feedback plus minus and the signal is coming x2. So added here is x1G plus minus x2. Okay. So what we have to do now? We have to shift this summing point ahead of a block. If you shift the summing point ahead of the block diagram will be like this. If you shift the summing point ahead of a block, the block diagram will be like this. But now see the output, it is x1G plus minus x2G. Okay, so the output is not same, just like this. So to make the output same, here we have to add one more block, and the gain of this block will be 1 by G. The gain of that block will be 1 by G. So what will happen? So if you multiply this, the GG will get cancelled, and what will remain there? It will remain there only x2 at this end. So at this end now the output is now same. That is x1 g plus minus x2. Okay, the output should not change by the addition, by the taking the summing point ahead of the block or after the block. Okay, so that is how we can use these rules for the block diagram deduction. Next is moving a take up point after a block. Now some take up point is there. Moving a take up point moving a take up point after a block. So this block diagram is given to you. The input signal is x1 and the output signal also going in this side x1, and now here what will be, this is a x1g. So we have to move a take up point after a block. We have to move the take up point after the block means we have to take this point here. So if you take this point like this, so this is your point. Now see, here it is x1 and 2g. Here the output is same, but here output is changing. Initially the output is only x1. Now here output is becoming x1 into g, that is a x1g. So for getting x1, we have to again multiply it by 1 by g. Are you getting what I am writing? So x1 into g into 1 by g, the output will again g. Output will be again here, sorry, x1. Output will be again x1. So this is how we have to add the block in the feedback system so that your output will not change. Here in taking the point after the block or before the block. So in this here we have take up point, we have moved the take up point after a block. So when you move the point after the block, so this signal is get also multiplied by this. So we have to make one more block and the gain of that block will be reciprocal of this gain, so that it will be get cancelled and the output will remain same, that is x1 here, and here output is also x1g. So this is the rule number 5. Rule number 6 means moving a take up point ahead of a block. So this one block is given to you. Okay, suppose the incoming signal is x1 and the outgoing signal is x1g. So here it is also x1g, but we have to move this point here. We have to move this point here, means ahead of a block. So if you move, your diagram will become like this: g. So this is x1 g, but whether this is x1, so signal is coming here x1, so it will be x1 only, so we will not get x1g, will not get here x1g. Here now it is getting x1, So we have to write here G, and therefore the output from here it is also x1g, and the output from is also x1g. Okay, so in this way we have shifted the take up point ahead of a block. So in doing so, we have to add one block in the feedback loop, that is G. So moving a take up point ahead of a block. Next is the rule number 7.
Yes, sir.
Bolo. Yes, any difficulty? Yes, somebody has said, want to say something? So next rule is eliminating a feedback loop. So suppose the some loops are there. This is summing point. This is a one block having the gain G. This is a feedback block having the gain H. And if such system is given to you, this is x1, this is plus minus, and this is a x2. So if such a feedback loop is there, then we can reduce this feedback loop to just one block having the gain input is x1, output is x2, and this gain we can write like this: G upon 1 minus or plus this G of H. So this is the plus sign is when the negative feedback is there, and a negative sign will be there when the positive feedback will be there. Okay. So but generally we have the negative feedback. In order to reduce the error in the systems, we have always the negative feedback, and whenever there is a negative feedback, the positive sign is always appears here. So the input is x1, output is x2, G upon 1 plus GS. So this block is having the gain G, this block is having the feedback gain H. So this is how we can reduce the given blocks into the simple or one single block, so that we can arrive at the transfer function. Now if anybody asks you to find a transfer function for this block, then this is x2 by x1, that is G upon 1 plus GS. Okay, so in this way we can reduce the system having the block diagram very complicated. Okay, so we'll take one example. The example is, there is a summing point. After that there is one block having the gain G1. After that there is another block having the gain G2. Again that there is a summing point. After that there is output C. Okay, so from this G2 there is again one block G3, and this is connected to the summing point. This is minus, this is plus, this is plus, and this is also one feedback loop is there. This is H2, There is also one summing point, and to this H2 block is connected, and this is connected here. Okay, so here it is a plus again, G4. So such system is given to you. This is the input and this is output. Now this is a negative. Okay, so such system is given to you. Now we have to find the transfer function of these systems. So what we'll do, prima facie, we can see these, we can say these two blocks are in parallel. Hey, you can see these two blocks are in parallel. So we can reduce these blocks and we can just write instead of this G1 minus G3. Okay, so what I will do, I will just remove this whole circuit. This I have shown in the dotted line just by the one block having the gain G2 minus G3, because these two are connected in parallel. So by using the rules, I can just use this. So this will become G2 minus G3. Okay, now it has become now simpler. Okay, because these two blocks were connected in parallel. Now what I will do, I will again see these blocks and these blocks, they are connected in series. I will again use the same rule. I will use these two blocks G1 and G2 minus G3. These two blocks are connected in cascade or in series. So I will just multiply the gain of this individual block. I will just multiply the gain of this individual blocks. So it will be like this. So I will just remove this and I will just draw one blocks, and having the gain of that block is like this. So I will remove this. And I will just write this G1 into G2 minus G3. Okay. So I have just two blocks were connected in series. So I have just taken only one blocks and I have multiplied the gain of that individual two blocks. Okay. So now again, what I can do here, I can shift this summing point after a block. So I can shift this summing point after the block. So when I shift this summing point after the block, what will be there? So this S2 will come. Okay, sorry, make one correction. This is S2 and this is H1. This is H1. Okay. So I have to shift this summing point after a block. So when I shift this summing point after the block, what will be the diagram will become like this. The diagram will become like this. We'll just draw this. This block will come here, H2, and previously H1 block was there. Your block will become like this. But now here, in shifting this block, here the output will become now H1 is coming on this side, H1, H2, and here G4. But here it will produce one more block in the feedback loop. It will produce the one more block in the feedback loop, because initially that block was here. Initially this S2 was here, and after that G4 N2H2, that signal is getting multiplied here. But now only G4 is coming here. No H2 is coming here because H2 is shifted here. So we have to produce one more block here having the gain of H2. Having the gain of H2 so that the signal will again same. So in this way, we'll do that. Okay, after doing this, what will happen? These two blocks are again in series. These two blocks are in series. So we can just multiply this gain of this individual loops by the only one block. So I can show here only one block and I can multiply this. Okay, so what was there in this block? This is a G4 and H2, here H2, H1. Okay, so now your block diagram is somewhat become simpler, or block diagram becomes somewhat simpler. Now what happens? We have to interchange the summing point. If you interchange the summing point, we can also write like this: interchange summing point. If you interchange summing point, your diagram will become G4 H2 this is G1 G2